9.2 is operations on vectors. Operations on vectors, we're talking about adding, subtracting, multiplying, dividing. Here we're basically going to be looking at scaling up a vector, so making it longer, shorter, or changing its direction to be the opposite direction. And then we're going to be looking at adding and subtracting using some different models. So here we're looking at what's called multiplying by a scalar. So the scalar is referred to as k here, and all it's going to do is it's going to stretch our vector. So this is our unit vector here of whatever a normal is for this particular vector. This is half of its length. This is twice its length. Here we've multiplied it by -1, so our scalar here is multiplying by -1. And that means that he's going to be starting where the other one ended here, turning the opposite direction. Now this point could be shifted down to the origin, and then it would be mirrored across the origin there, if you wanted to look at it on the coordinate plane. This guy here also has been multiplied by a negative scalar, which means he's going the opposite direction, and he's had a stretch on him. So the original u, and then half of that u also, making it -3.5 u. So that means that when we're looking at vectors, okay, they are going to be parallel if there is a scalar multiplier between these two vectors. So any of these vectors would be considered parallel because this vector and this vector are the same in direction, but this guy right here is half the length. Okay, so if I have some original vector u sub 1, u sub 2, and then I multiply it through by a scalar, and that's going to be called vector v, then k times each component gives us k times u sub 1 and k times u sub 2. So that's a little bit confusing, but if we look here at example A and B, 3 scaled by 2 is 6, and -4 scaled by 2 is 8. That means that if I was going to graph these two, they would be parallel vectors. However, none of these others have a scalar on them, so they are not equal. But these two right here, parallel. Okay. The magnitude of this, 3, 4, that means it's a 3, 4, 5 triangle, so that's going to be 5. 6, 8, 10. Here we go. That's another 3, 4, 5 triangle, just scaled up by a factor of 2. And since 3 times 2 is 6 and 4 times 2 is 8, that means that the hypotenuse, or the length of these triangles, would be also times 2. So since the vector v is twice as big as the vector u, then v's length is twice as big as u's length. Here I'm just looking at 7 squared plus 0 squared. Well, that means it's just 7. That's just a horizontal vector. He doesn't have any vertical shift at all on him. And then this guy right here, 1/2 and √3/2, those seems like values that maybe are familiar to us. That's because they're on the unit circle. And when you notice that we get the hypotenuse of that point, we're getting 1, a unit vector, because it would be a vector that begins at the origin and ends at a point on the unit circle. Also unit because it has a length of 1. The unit circle shows up over and over and over again, you guys. Okay, so we're going to look through one example here, example 5. I'm going to work it out for you. We're going to do some drawing, which will be kind of fun. So let's look here on the presenter, and we'll go full screen. All right. So we're going to look at u and w. Okay, and then it says, if vector v is 2 times vector u, what is vector v? So I'm going to take 2 times each component of vector v, which means that v is going to equal 4, -6. It's a scalar on each component. Here we're going to be determining the magnitude of u and v. Well, the magnitude of u is going to be 2 squared plus 3 squared, square rooted, and since this is negative, I'm going to be squaring it anyway, so it doesn't really matter. I can ignore that. So 4 plus 9 gives us root 13. And since v is just twice as big as u, then the magnitude of v is going to be twice the magnitude of u. Okay. We're going to do some drawing now, so let's look at the coordinate plane here. So we're going to draw u, vector u. So u starts at the origin. It's going to go 2, -3. So here is u. And v is basically the same one here, only it's coming down a little farther. So this whole thing is v. W is 1, 3. 2w would be up here. So it's w and another w. U plus w. Well, let's do u plus w algebraically first. Let's just do the arithmetic for it. So I'm going to be adding together the components of each one of them. So the y components are going to give us a 0. The x components are going to give us a 3. So 3, 0. Right there. That is u plus w. V plus 2w. V is 4, -6. 2 w's. 2w, well, w is 1, 3, so 2w would be 2, 6. 2w is 2 times 1, 3. So that means when I add these together, I'm going to get 6, 0. Right there. Shift that up a little for you so you can see. There's another u minus w. So 2, -3 minus 1, 3. So 2 minus 1 is 1. -3 minus 3 is -6. Be careful. So 1, -6. There's that guy right there. That is u minus w. And then we're going to do v minus 2w. So 4, -6 minus 2w, which we calculated up here, to +6. So 4 minus 2 is 2, and -6 minus +6 is -12. So we're going to go to oops, this guy right here should be right here. That's right there. And then 2, -12 is going to be down there some little bit further. V minus 2W. So then it asks us to comment on what we see here. So what I'm going to show you is that anytime we add two vectors together, right? So if I had this vector plus itself basically, or times 2, I'm seeing it get longer but maintain the same direction. Same thing here. If u plus u, or 2u, is equal to 1v, then it has the same direction, but it's twice as long magnitude. And then anytime I have things that are have the same direction, or they have the same direction, they could be considered parallel. So this one and this one, if I were to shift him anywhere on the plane, they would be parallel. Back here, we're going to look at some models for vector addition. So this is referred to as the triangle method, where it's just head to tail, u, and then you move v so that it's ending here and starting at the end of this one. And then we're going to look at the parallelogram method because we haven't done that before. This is the one we've been practicing in class, but we'll try both of them to do some different questions. So I'm going to shift this guy up here. So we're going to look at adding two vectors together. We're going to do the triangle and the parallelogram method, and then we're going to look at some different notation and show how to visually or algebraically show it versus visually show it. And I think we're going to have to do that on the next video. I think we're running out of time here.